Hi, good morning, everyone. I'm Jeff Yee, and my presentation is the relation of electric and magnetic field laws to matter laws. Now, this was co-developed with Lloyd Gardy, who's not here today, but a lot of credit goes to Lori for providing the connection on this relation, which I will explain as we go along. So first, a quick summary of what I'll be covering today. In our presentation, we will show that 4 matter laws will be shown to be the equivalent of field laws. And the matter laws you can see on the left side includes Einstein's mass energy equivalence and 3 of Newton's laws. And they are related to electric and magnetic laws, Coulomb's law, the electron's magnetic moment, and new induction and new magnetism, which comes from Robert Vistinti. This is a lot of the work that Lori did connecting it. I was not familiar with Robert's work on new induction and new magnetism. I was actually trying to relate these to Maxwell's equations and having a difficult time when Laura came to me and said, hey, why don't you try new induction and new magnetism? So on the left, the laws that are filled with M for matter, and charge Q represents the field laws. So before I get into the actual relationship of all 3, I'm going to go through, all 4, I'm going to go through 3 slides that are basic principles to understand first. The electron is often pictured as a spherical object, something distinct, but the matter laws use the mass property M, field laws use the electronic property Q. What we found is that the forces for both matter and for fields are equal when using a single electron at the distance which is the electron's classical radius. And I'll prove this for at least 3 of the 4 numerically and mathematically in just a little bit, but a couple more slides on basic principles first. Now, if we assume that everything are waves, that's what would be the common point between matter and fields. If everything is formed from waves, the assumption here is that the electron's energy is standing waves, made of both in-waves and out-waves, and that beyond that point is the transition to longitudinal traveling waves. Any distance from that particle can be calculated as a force, and that's the R in the equations that you'll see in just a second. The last thing on basic principles before I start to go into the relationship. I've used a lot of icons here as we represent both longitudinal waves and transverse waves. A longitudinal wave amplitude is in the direction of propagation of the wave, and in transverse wave, of course, is perpendicular. Now, the concentric circles icons that you'll see in the following slides represent a standing wave. That we see as the arcs there represent longitudinal traveling waves. And then finally, the red ones you see there are transverse waves. It's really a spin. Okay, so then now let me get to the fun stuff. So the first of the 4 laws that we will show are related are Einstein's energy and Coulomb's law. Now, first you're going to say, all right, that's an energy and a force, and I'll explain that on the next slide. But this is what you're going to see as the icons for all 4 of these as we go forward. You can see it represented there as the particle on the left is represented as concentric circles. But if you go beyond that, we know that an electron has a force, and that's represented by these lines that are longitudinal traveling waves. Now, to relate these two, as I mentioned, everything that we found is related to the electron's radius. And so if you take Einstein's energy and you basically take it as a ratio of the electron's classical radius to the distance that you're measuring it, and then square that to become a force. Do this for a single electron at the electron's radius, that's the RE, and then on the right side you see the Coulomb's force. It's the Coulomb constant and the single electron charge, otherwise known as the elementary charge. Do this for any distance, and you'll find that these 2 are equal. And this is simple enough that everyone with a calculator in the room can reproduce this. I chose 4 values of R. It'll work for really anything, and you'll see that that any R value that you choose, these 2 are exactly equal. Now, there's something highlighted in red there, which is the electron's radius, and this is going to show up in the 2 of the next 3 slides. So remember 29.1 newtons, which is the force exactly at the electron's radius. Okay, so that's number 1. the relationship between Einstein's energy and the Coulomb force. And the important thing is that was a at rest, for a particle at rest. One other thing, and this ties to some of the work that I have been doing, is working on expressing everything in terms of wave constants. And so in energy wave theory, these equations, both on the left and the right, Einstein's, the force version of Einstein, as well as the Coulomb force, derive to a single equation when expressed as wave constants. Now, I'm not going to get into all of these, but you see constants like density and a wavelength and the A there for amplitude. I've left a URL in the bottom right there. You see energywavetheory.com/equations, and you can see the values for each of those constants. Okay, but instead, I'm going to focus on just the known laws, in this case, Einstein and Coulomb's law, and relating them. Now, I mentioned that 4 and 3 of the 4 are quite easy. This next one's actually probably the hardest out of all of them, because I can't express it numerically, but it is an interesting relationship, and so I want to mention this one briefly. Newton's gravitational law, the universal law of gravitation, is related to the energy of an electron spinning, otherwise known as the electron's magnetic moment. So you can see the common law for gravitation there on the left. That's matter law. It has m for mass in there. And on the right, the field law there, that's the symbol for the electron's magnetic moment, otherwise known as the magneton. Now, how are these related? If you take a single electron at the electron's radius, and that's what you see on the left-hand side, we're going to do that for energy form, not for force. You see a very small amount, 1.9 times 10 to the minus 56 joules, very small amount of energy. What happens to be the magnetic energy, you can see the magnetic constant, the Planck charge, and 4 magneton in here. There's a couple of other constants that come from energy wave theory in here. So again, this is probably the hardest one out of the 4 that I'm going to show. But assuming you understand the additional constants for energy wave theory, the important thing is that these are exactly equal. And they're equal, again, because they derive to the same equation when it's represented in terms of wave constants. So that's 2 of 4. Now the next 2 become a lot easier again. But now we get into motion. So that was in a longitudinal wave and a transverse wave for a particle at rest. Now, electromagnetism. And I'm going to cover induction and electromagnetism. One is in motion for a longitudinal wave. The representation of matter law, of course, is Newton's second law, F equals ma. And as I mentioned earlier, I was having a difficult time trying to relate it to Maxwell's equations until Laura gave me today. I think the connection is actually with Robert Distinti's work. And so what you see on the right is Robert Distinti's new induction equation. And again, you see a particle represented on the left, but now in kind of waveform on the right. And now in motion, that particle experiences the Doppler effect. That's why you see the amplitude and wavelength changes on the left versus the right, depending on the direction of motion. So now getting back to calculations, and just to easily prove that, that these 2 are equal, again, the common thing is at the electron's radius for a single electron. So here we use a single electron mass, a single electron charge, and the electron's radius. Now, when you use those as the constants in these equations, choose any value of A. Again, I've arbitrarily shown 4 here in the calculations, but choose any value of A acceleration, and you're going to find that these forces are equal. But again, it's only equal when measured at the electron's radius, because you notice on the left-hand side, force is not decreased based on distance, whereas on the right side it does. And so you have to use the electron's radius. And again, you see it highlighted in red, that 29.1 newtons. It occurs when acceleration is c² divided by the electron's radius. Okay? Now, once again, the reason why these 2 are equal when expressed in terms of wave constants is they're exactly the same thing. These equations are the same. One thing to note, though, is you notice I've changed from F to E. That's good. It's gone from a force equation to energy. How to do that? Because the only way to make these equal is conservation of energy, but the only way to do that is to write it down to energy, because the forces are only going to be equal at the electron's radius. Okay, now the fourth one. Now it was longitudinal waves shown in the icons. Now in motion, a transverse wave amplitude changes for an electron in motion, electromagnetism. And this was related to another of Newton's laws, which can be derived to centripetal force. So you see that on the left as the matter law. On the right side, you now see another of Distinct's equations, and this is specifically his point particle form for new magnetism. Okay. So now the particle spins faster, it has a spin wave change, and to prove that these two are equal mathematically, do the following. Again, use the electron's radius, use a single electron mass, and use a single electron charge Q. And you'll find that you can choose any velocity v. That's the only variable that's left. You can choose any velocity v, and they will always be equal. Again, I'm just showing 4, but choose any velocity that you want. Here again, you see that 29.1 newtons, and it occurs when the velocity is equal to c, the speed of light. So, and then once again, you can see in energy wave form, the reason why these two are equal is it's exactly the same when expressed as wave constants. So those are our 4. We related those 4, 3 of which are quite easy to reproduce, given Robertson's equations, given Newton's equations, given Einstein's equations. So it took us one step further after doing those 4 and recognizing that everything was essentially related to these properties. Everything was related to the electron's mass, or you can also do it in terms of energy, E. The only difference, of course, is the c squared. But all of these were related to electron's mass and its radius. Right, all those equations we've discussed. And the 2 different types were either longitudinal or transverse in form. And then, of course, the reason why there's 4 is one was at rest and the other was at motion. And she ended up with 4 different laws for both matter and for the fields. But for forces, we had to add a few new variables. It's typically based not just on a single electron, but we do measurements based on multiple particles. So the particle count, capital Q instead of lowercase q, was added to the equations. That affects the wave amplitude, is constructive or destructive. And of course, since in many of the forces, the force decreases based on distance, or the square of the distance, the distance r is required to understand what the effect is on wave amplitude. And one last thing, which was shown on only the second relationship, which is an amplitude loss or gain from a wave type conversion. So this alpha symbol is used. It's the coupling constant in physics. So given this, here's what we did. Summarized the first 3 that you see there were shown earlier as a relationship: Coulomb's law, Distinct's magnetism, Newton's gravitation. Took that and just summarized it in terms that are very familiar to everyone, which is electron's energy, the mass of the electron, or the classical radius, Re. And you notice that there's a pattern here, right? Coulomb's law is that first one, but you notice that you go from Coulomb's law to Distinct's magnetism. The only difference there is, instead of representing E as an mc squared, it's represented as mv squared. By the time you get to gravitation, the only difference between that and Coulomb's law is that coupling constant. The difference between the strong force and what's called an orbital force, explained in another paper, again, is just related to a coupling constant. So we tried to take forces and to write them down to something that'd be much easier to digest, and you see an interesting pattern here. So I want to wrap this up with just a few more slides. That was the work we did with the equations and just relating it and plugging in some numbers. Trying to make a little bit of sense on this visually, what's going on with magnetism. So I've got about 4 or 5 slides, so I'll just wrap up here. So at rest, which you saw from from the Bohr magneton slide where we related it to gravity. At rest, the electron is spinning. We know that there's fields that can be found from magnetism, even ferromagnetic materials where we know the electron is probably at rest. But now couple that electron with a proton, dipole, and the waves change, the fields change, and I'm assuming here that it's destructive wave interference or constructive wave interference depending on the direction of spin. So that's sort of represented here as the electron and proton. Now, imagine those two are at rest in an atom, they're stable, but all of a sudden, something happens that causes wave amplitude, such as induction, right, a current flowing. Now, with higher wave amplitude, and this is one of the basic principles within the energy wave theory, but motion is a result of a particle moving to minimize its wave amplitude. So as a particle is in motion from left to right, you see there one particle that affects a stable electron in orbit. Now, one thing that's missing here is we had some animation in this slide. I missed that animation, but as a particle that moves from left to right, it separates from its from the proton it was connected to. It's now moving along in a wire, and it will be now connected to the next proton. The electromagnetism, the direction of the current, you can see there goes from left to right, but now as a particle spins, you saw that from the fourth law that we did the relationship for faster spin from the centrifugal force now has a higher wave amplitude because the energy of that spin is higher. And therefore, if you compare that now to a proton that was connected to that amplitude for the transverse wave should be either greater or it should be lesser, depending on the spin. It's going to be either constructive or destructive. That force direction, the waves are going to collide at many different directions, but the point between these two particles is going to be the strongest. And so therefore, the direction of the force should be perpendicular. And it should go one of two ways depending on the spin. Right? And in the spin, it's either going to be constructive or destructive. And so this is explained in experiments that show basically the spin of electrons. All right. So that's just my attempt. This last part is just my attempt to visualize everything that we learned. So let me just conclude what we did find. Right? 4 classical equations that were all based on matter can be shown to be the equivalent of field laws, and all of those are distinguished by charge. So one has m in the equation for mass, and the other has q in the equation for charge. Now, 3 of these 4, numbers 1, 3, and 4, numerically from what I've shown, are easily demonstrated, right? You can do it yourself by just plugging in a single electron's mass, charge, and radius into the equation. The equations are going to be equal when the force is measured at the electron's radius. Now, 2 of the 4 relationships use Robert Distinct's equations for new induction and new magnetism. And I think maybe that's the reason why this hasn't been discovered until now. The relationship between Distinct's work and Newton's work actually should hopefully help to validate Robert's work. But lastly, there's a relationship between all the forces. There's actually 2 that I summarized at the end that were not covered here, but I do have papers for the strong force and also for orbitals. And the pattern that emerges is, again, it's just related to a single electron's mass, charge, and radius. And that was it. Hopefully you find that interesting. Like I have, I was actually amazed when Lori first brought it to me and kind of worked out some of the numbers. It's kind of fun and fascinating to work on, and I hope you find it too. And with that, I'll turn it over to David. I'm happy to take any questions.
Okay, can you hear us?
Yeah, just fine.
Oh, great. Boy, that's half the battle. Okay, you can see, let's see if we can maybe stop displaying this. Oh, boy, no, I don't. Try to figure out how that goes. Can you use your mic, David? You don't. Yeah, you guys need to use mics so he can hear you. How do I get him to be bigger and this go away?
You might grab a hold where the dots are. You might grab a hold of that, see if you can pull that down, and then maybe double click on his picture. I don't think I discovered a way to make this picture full screen, really.
Okay.
That doesn't grab. No, that's well. I made the presentation full screen. Try and do the opposite.
Stop sharing. There we go.
There we go.
Okay, questions. Please get a microphone. Turn your microphone on. Put the microphone up to your mouth. Okay?
I have a question. I'm Cameron Redixel. This seems from your presentation, I have three impressions. Number one, you have to base your idea about mass on the idea of mass on the relativity's idea, E equal to mc squared. The next impression, it seems to me that electron is a source of energy, keep radiating energy, both in a wave of longitudinal and transverse. The third impression is that electron is also the source of diamagnetism and paramagnetism. And then further, I wonder how that much stronger ferromagnetism will be resulted by the electron. And am I right or wrong in getting this impression from your presentation?
Yeah, I think you're correct. One thing I didn't do the details of the theory that I've been working on. Try to stay with mostly just the facts that you can see for 3 of the 4 of those are just simply got the numbers between known equations. But I think if you were to dig into the details of the theory that I've been working on, I think you've got the right impression, yes.
In that case, I have to be sorry that personally, I cannot accept relativity, particular special relativity. It is a self-refuted theory. And in that case, in case, relativity is really proven wrong, I think your theory may have to reconsider a new base to formulate your theory. I'm so sorry to say that. Of course, you can say I am wrong if I say relativity is wrong.
Yeah, but I'm sorry, you were trying to compare this to relativity, correct?
I'm sorry?
Sorry, you're comparing this to relativity? I'm trying to understand the question.
Okay, it seems to me that you base your mass concept on the concept proposed by special relativity, E equal to mc squared. Again, to me, special relativity is wrong, and if it is really proven wrong, possibly your theory has to start from another base. But of course, you can say what I see relativity wrong is mistaken, and then you can say I am wrong. That's your freedom and your decision. And I just say that I disagree with relativity, so that I cannot have agreement on your concept E equal to mc squared.
Yeah, I appreciate your comment. Keep in mind that was the E equals mc squared is one of only 4. There's a similarity across many different matter and field laws here, and I think you're just picking on one of the 4. Relativity as a whole, whereas I can understand if some people want to challenge all of relativity, the part that you're referring to, which is equal to mc squared, I think has been validated many times by experiments. So all I simply did was take the equation and relate it to Coulomb's law, both of which have been experimentally verified.
Possibly, I cannot argue with you in this presentation because the time is so short. I appreciate if you can give me your email address so that we can discuss a little further.
Yeah, happy to do that. David has my email address.
Okay, I will ask David for the email address. Okay, thank you very much.
Well, Jeff, give them your URL. He has not only a website with everything on it, he also has a YouTube channel that we support because he's a member of our organization that has a very, very beautiful explanations of his theory, which he hasn't really talked about here. I understand a lot more because I've read it and seen everything he's been doing. So I would encourage you to go. Is it energywavetheory.com or?
Yeah, that's correct.
Okay, so you can take a look even on our homepage on the right side. You'll see energy wave theory. Click on that, and you will get really beautiful videos describing this whole theory of his. And his website has. You have a book, it's really free, right? Why don't you say a little bit about that?
I have 2 books on Amazon as well, in addition to the website. Free, there's a charge part, but I think it's such a low price.
We're getting parallaxing with you're going along, can you say that again?
Yes, there's 2 books on Amazon. Am I coming through clearly now?
Well, no, we're getting a parallax where the thing goes through a wave transformation where it's like.
All right, let's try it without the headset. Was there any difference now?
100,000%.
Oh wow. Okay. All right. Yeah, just a short answer to that question. There's a couple of books on Amazon. Particles of the Universe series you can find on Amazon.
David?
Okay, more questions here.
Yeah, Duncan Shaw. A question about, I think the first diagram that you showed, it showed the electron, and it showed waves emanating from the electron, surrounding the electron. My question is what are those waves going through? Is there a medium for the waves, or what's physically happening in that area surrounding the electron?
Yeah, I purposely stayed away from either discussion for this because I wanted to highlight basically the relationship of Distincti's laws to matter laws. But since we're getting into what I believe and where those waves are traveling, I do believe in an ether. I believe that those waves are traveling, both longitudinal waves and the transverse waves need to travel through something, and I'm an etherist.
Thank you.
Perhaps 2 questions here. Carl,
if you're speaking, I can't hear you right now.
I'm Carl Itteman, and perhaps 2 questions.
Can't hear.
Oh, sorry. I had you muted. It's my fault. Go ahead. I had you muted.
Okay, I'm Carl Itteman, and I have a few questions. And some of the CNPA answers here are trying to get rid of the term strong force that holds the atoms together, such as the helium nucleus together, and instead of going with a strong force, they want to just go with electrical forces and do away with so-called nuclear forces, which they would hopefully, they hope that they can show just arise out of electrical magnetic forces. So my question is, do you believe that nuclear forces are caused and arise from something other than electrical forces?
No, I think that they come from electrons. I think that it appears Coulomb force on a traveling wave. I think that when you're within a standing wave, then it becomes either the strong force or the nuclear force, and the only difference is the distance between those two, the strong and the nuclear.
Okay, and of course, I think you said, but things were a bit blurred. The radius of the electron that you're talking about, I think isn't that the classical radius of say roughly 2.84 times 10 to the minus 15 meters, and not the Compton size, that's more like something like 10 to the minus 12 or 13 meters.
Yeah, it's correct. Not the Compton, it's the radius, which is 2.8 times 10 to the minus 15 meters, correct.
Okay, maybe one last thing.
Hold on.
Are we on mute again? I can't hear.
Go ahead. No,
Okay,
my bad.
you use the term spin, and that's important in your concepts. One might momentarily ask or wonder, well, why doesn't the spinning electron or the spinning proton fly apart due to centrifugal considerations or whatever? And I imagine ultimately you use your charge and the concept of electrical properties to kind of pull it in together and keep it from flying apart. Is that roughly true?
Yeah, to keep it from flying apart, the forces that hold it together need to be much stronger. I mean, similar to particles on Earth being held in place instead of spinning off of Earth.
Okay, thank you.
Yes. Okay, if you have your mic, just go ahead.
Yes. Coulomb's law, as you stated, is it independent of speed of the particle, of the charges?
Sorry, is there speed of the particle?
Is Coulomb's law independent of velocity of the charge?
Yes. When a particle is in motion, then it changes to be the law of induction.
Secondly, in a moving electric charge, where is the kinetic energy located?
You're cutting in and out. I think I'm only getting part of the question.
Go ahead, try it again. We have
In a moving electric charge, where is the kinetic energy located?
The kinetic energy would be in the mass of the electron.
Did that answer your question?
Yeah. Thank you.
Okay, another question?
All right, Duncan Shaw again. You spoke of the spin of the electron, and it's essential to your reasoning, obviously. Is it necessary that the electron have spin? Might it be vibrations of the electron that are at play?
Yeah, I certainly wouldn't rule that out. In my presentation, you noticed there was the first part that was equations of just plugging in numbers to prove that those equations were equal. The second part was my interpretation of what might be happening. I made an assumption, that is, transverse waves due to spin. But again, that was just my interpretation of the results.
Thank you.
More questions? Any more questions? Okay. I want to thank you. You can hear me, Jeff?
Yeah, I can.
Okay.
Yeah, I just want to say thanks to everyone. I appreciate the questions and also the time today for allowing me to present.
Okay, and can you tell them once more where they can find your work?
Well, yeah, I actually want to get a plug also for Robert Distinti's work, because again, this presentation was really more about relating Newton's laws to his induction and magnetism equations. Robert's work is at Distinti, DISTINTI.com. My work is at energywavetheory.com.
Okay, well, listen, thank you so much. I do appreciate it, and we hope to see you next year in person at our conference. I guess you really couldn't make it because of the some conflicts at work, correct?
Yeah,
so,
that's correct.
We hope to, and I do encourage everybody to take a look at his theory. It's quite complete. So, and we're very happy to have you on board here, and thank you so much for taking your time. And I'm sure people can contact you with specific questions.
Yeah, I'd be happy to take any additional questions. Yep.